In this video, we're going to learn about the history of atomic theory. In ancient Greece, Democritus came up with the first philosophical concept of an atom, though it wasn't until 1803 that John Dalton came up with the first scientifically based atomic theory. And he stood on the shoulders of Joseph Proust and Antoine Lavoisier in coming up with this idea of the atom being an indivisible billiard ball. About 100 years later, J.J. Thomson discovered the electron. He experimented with cathode rays, which at the time were not very well understood, and he found out that those cathode rays were actually electrons that existed within the atom. In his experiment, Thomson found that the cathode rays were negatively charged, and he also proved that they were particles. And so from this, he came up with the plum pudding model, which is essentially that the atom is not a simple indivisible billiard ball, but it's a ball with positive charge, and interspersed within this positive charge would be these little electrons. Around the time that Thomson was studying cathode rays, Marie and Pierre Curie were studying radiation, and their work led to Ernest Rutherford's discovery of the nucleus. Rutherford is most famous for the gold foil experiment, in which he fired alpha particles at a thin piece of gold foil and found that most of the alpha particles ended up going straight through, although some of the alpha particles deflected off to the side. Rutherford theorized that most of the mass of the atom is in the very center and that it's positively charged, just like the positively charged alpha particles. That's why they bounced off. He also theorized that the atom is mostly empty space since most of the alpha particles went straight through. So in 1911, just 14 years after Thomson's model, Rutherford came up with the solar system model, which is shown here. But there were two big problems with Rutherford's model. The first was that the mass of the atom was not equal to the mass of the positive charge in the nucleus alone. And the second was, well, why didn't the electrons just spiral into the nucleus? What was it that kept them in motion? Now, to the first problem on the mass of the atom, it wasn't until 1932 that James Chadwick discovered the neutron. This actually came after pretty much every other discovery of the atom, but it was difficult to find the neutron because it didn't have a charge, and it was essentially invisible to any type of probing that you might do with charged particles. To Rutherford's second problem, here's an example of his solar system model with the nucleus here and the negatively charged electron being here. Well, if just allowed to run out, you'd think that the electron would simply spiral into the nucleus and pretty fast the universe would just explode. Which of course isn't the case. But he didn't really have an explanation as to why the negatively charged electron and positively charged nucleus didn't just come together. Enter Niels Bohr, the father of early quantum mechanics. Bohr experimented by running electrical current through hydrogen to excite the hydrogen. The hydrogen glowed in the same way that a neon light glows, but he put a prism in front of the light so as to separate the different wavelengths of light that were emitted. And unlike many other sources of light, like a classical incandescent light bulb that would give you a full spectrum, he found that only certain specific wavelengths of light were emitted. What Bohr proposed is that these wavelengths corresponded to transitions between the electron being in one energy level and another, but that these energy levels were quantized. It wasn't that the electron could exist at any level of energy, there were only specific quantized levels at which the electron could exist. And the wavelength emitted corresponded to the difference in energy between those two levels. For example, an electron in the third energy level transitioning down to the second energy level would lose some energy that would be released in the form of a photon that has a wavelength of 657 nanometers. For a larger transition, like from the fourth shell down to the second, the wavelength of the emitted photon would be shorter, corresponding to a higher energy of that photon, with the wavelength being 486 nanometers. Now, Bohr's research was groundbreaking, but it also had its shortcomings. We can see here the electron is simply orbiting in a very predictable pattern around the nucleus. If it were excited, maybe to the fourth shell, then it would simply rise up and go around in another very predictable pattern. But in 1924, Louis de Broglie proposed that all moving objects behave as waves. And on that assumption, the electron can't simply go around in a circular pattern, it behaves partially as a wave. Around the same time, Werner Heisenberg came up with the uncertainty principle, which was that you cannot simultaneously know the position or the momentum of anything, especially an electron because it's so small. And as you come close to knowing the position, you become less certain of the momentum. And the key here with momentum is really the directional component of it. Also, as you become close to knowing the momentum of something, you lose track of its position. Heisenberg's uncertainty principle is that the product of the uncertainty in position and the uncertainty in momentum is greater than or equal to h over 4 pi. And this was essentially the final nail in the coffin of Bohr's model. Because Bohr's model had that the electron simply goes around in a very predictable orbit, but that can't be true because the electron is a wave. Moreover, this predictable orbit is completely inconsistent with Heisenberg's uncertainty principle. Per Bohr's model, it's very easy to tell where the electron is and where it's going at any given moment, but Heisenberg was able to prove that you can know neither, and as you get close to knowing one, you become very uncertain of the other. Then came Erwin Schrödinger, who came up with the wave equation. He proposed that the electron does not exist in a simple orbiting pattern, but rather that there is a probability cloud. This orbital, as he described it, was a region of space where the electron is likely to be found, but you can't be 100% certain of where it is at any given time. And so if we look at Schrödinger's model, we can have an electron existing with 4 quantum numbers. These describe the energy level, the shape of the orbital, the orientation of the orbital in space, and the spin of the electron. So if we look right now, we have a hydrogen atom with its electron in the first energy level, and it has a set of quantum numbers. If we shine light on it, then the electron might go into a higher energy level, which I'll pause right here. The electron absorbed energy and went from what's called a 1s orbital to, in this case, it was in the third shell, and it actually moved to a 3p orbital. We can see that the shape is different. It's no longer a sphere, but rather there are 2 different lobes. It almost looks like an hourglass on its side, or the infinity sign. That electron will relax down to its ground state, and in the process, it releases a photon. So similar to Bohr's model, but different in the sense that the electron does not simply travel in a predictable pattern. Where Bohr introduced energy levels or shells, Schrödinger introduced subshells. So there were S that were spherical, P that looked like the infinity sign, and they were in 3 different orientations on the X, Y, and Z axes. There were D, which kind of looked like 2 perpendicular p orbitals, and then the F subshell, which in its 7 different orientations just looks quite complicated. Schrödinger's model takes Bohr's principal energy levels and then splits them such that the 2s and the 2p aren't of exactly the same energy. Note that within any principal energy level, the s is the lowest energy, followed by the p, the d, and the F is the highest. Also important is the fact that the first energy level only has an S, the second has an S and a P, the third has SP and introduces the D, and the fourth principal energy level has SPD and it introduces the F. This can be used to explain why the periodic table gets broader as you go down. In the first energy level, there is only the S subshell, and there is only 1 orbital within an S subshell, and that orbital contains 2 electrons. When we move to the second energy level, there's not only the S, but also the P, and the P has 3 orbitals. In total, the second energy level has 8 electrons in it, contained in the 4 orbitals that are the 2s and the 2p. When we go to the third energy level, we have not only the S and the P, but also the D. The D offers 5 new orbitals, holding 10 electrons, in addition to the 8 contained in the S and P, which is why the third energy level holds 18 electrons. And the fourth energy level introduces 7 new F orbitals, containing 14 electrons. Add 14 to the 10 from the 4D, to the 6 from the 4P, and 2 from the 4S, and you get 32 electrons that fit into the fourth energy level. Schrödinger's quantum mechanical model is essentially the model of the atom that we use today, though, as previously mentioned, it was after this that James Chadwick discovered the neutron. That was the final piece of the puzzle, but much of the atom was understood through Schrödinger's model. So that's all for this video. I hope it's been helpful. Feel free to leave any questions or comments in the comments section below, and thanks for watching.